Good morning, good afternoon, or good evening, whenever you happen to be watching this. This is another lesson on mathematical integration. So this is going to be pure chapter 13.4, which goes with the notes, which you can find on Padlet. Please do find them. So we've talked up to now about integration as being the reverse of differentiation. We've integrated some simple functions, and we've also talked about the constant of integration. Now here we're going to take this more forward and talk about the concept of a definite integral, where we integrate between two particular points. But before we do anything, as you might be able to guess, I've got a few warm-up questions for you, and here they are. So if you could please pause the video now, attempt them, get them written down, and then check your answers only after you've attempted the questions yourselves. Here they are, as you can see. And so right now I'm going to run through the solutions to these, starting of course with question 1. So question 1, we need to find this integral of this particular function. And so what I'd suggest we do first of all is to simplify this integral by expanding out the brackets and getting any variable in its index form. And so if we square root the square root of x, we're going to get x. We'll then get double the product, so we'll get two lots of the square root of x, but like I say, in index form, that's x to the power half. Finally, we get the square of 1, which is just 1, dx. So now, like I mentioned in the previous video, we can partition this into its separate forms. You don't have to write this down all the time, and so I could write this down as, so I'm going to put in brackets, what this could be written down as. But I'm going to just suggest at this point that we can skip this step I'm doing in blue and move on to a quicker way. We can skip this and do what I'm going to write now in black. So give myself a bit more space. So bear in mind, this is one and the same as what I'm writing in blue, but we can just skip ahead and do this now without having to write the blue line. And so if we integrate x, what we're going to get is the power of x increased from 1 to 2. Then we're going to divide by that power of x. So it's going to be half x squared. We're then going to have 2x to the half. The half is going to increase to 3 over 2, and we divide by that new power. So all of that over 3 over 2. When we integrate a constant, we just stick the variable on the end of that constant. So 1 becomes 1x, which is obviously just x, plus c. So let's neaten this up ever so slightly. So we have half x squared. 2 divided by 3 over 2, that's going to become 4/3. X to the 3 over 2. Plus x plus c. Where c is the constant of integration, which we're going to talk a bit more about today. So question 2, based on what we just worked out on question 1, we're going to use our answers to question 1 to answer these questions here. And so if I just take what we had from question 1 and copy it across so we can work it out without having to just go back and forward between screens, which would be a slight pain, wouldn't it? Let's just take this here and bring it forward to this screen, like so. Okay, so that's what we had from before. This thing here is, oops, I'll undo that. Didn't mean to quite delete all that. This is the integral from before. This is what we ended up with. So first of all, we're going to evaluate this when x is equal to 0. Okay, so we're just going to take this, I'm going to substitute in what this is equal to when x is 0. So that would be a half times 0 squared plus 4/3 times 0 to the power 3 over 2 plus 0 plus c. Now if you're thinking ahead of me here, well that's just going to be c, isn't it? Because 0 to any power is just 0. Well of course you're going to be right. I'm just trying to show you this convincingly. So I'm slightly hoarse today. By horse, I mean my voice. I don't mean I'm actually turning into a horse. I am not a Shetland pony. I am Mr. Bailey. So yes, here I am, just integrating this. The 0 terms will just eliminate, and then we'll just be left with, of course, just the constant of integration on its own. We're now going to do the same when x is equal to 1. And so if we substitute in x equal to 1 into this expression, which we derived from the first question, we're going to have half multiplied by 1 squared plus 4/3 multiplied by 1 to the power 3/2 plus 1 plus c. Now, similar to when we were doing powers of 0, powers of 1 are also pretty damn easy to deal with. 1 to any power is just going to give us 1. And so what we're going to have here is a half plus 4/3 plus 1 plus c. Now, if we're a bit rusty from our adding up fractions from GCSE, not to worry too much. We have this calculator here to help us out if we should need it. So half plus 4/3 plus 1 is actually 17/6. So we'd have over here 17/6 plus c. Now again, if you think I'm lying to you, I'm not. I wouldn't do that. I'm just going to show you that it is 17/6. I worked it out before. So 1/2 plus 4/3 plus 1. There we go, 17/6. Obviously plus the constant of integration. Now, part C of this question is going to be a fundamental idea today. We're going to evaluate the difference between the answers to part B and part A. Now, the difference between any two things is just what we arrive at when we do one thing, take away the other, going back to pre-GCSE here. And so for part C, all we need to think about is our answer from part B, subtract our answer to part A. And so if we just take 17/6 plus c, and then minus off the answer from part A, c, the c's are going to cancel out, and we're just going to be left with 17/6. So this is a really important concept which you're going to be using today and now on. If we integrate between two different values for the same integral and then do one value subtracted from the other, the constant of integration just vanishes, and so our result is going to be independent from this constant of integration, which is a lovely result. We don't need to work this out, we just know that it's going to be independent of that anyway, and so that's going to be a really useful and powerful result. So for part C, we didn't need to actually know this constant of integration. Question 3. A driving test centre codes the times taken to complete a theory test in minutes by subtracting 2 from each of the times and then dividing through by 10. The coded mean, x bar, is 3.7 and the coded standard deviation is 1.4. Find the actual mean and standard deviation. Okay, so what I'm going to suggest we do is think of it like this. So we have two variables. We have a variable x and a variable t. And so these x values, we're taking the coded times, t, sorry, the actual times, not coded times, t. We're subtracting 2, which we have here, and then we're dividing through by 10. So just have this considered. So the actual mean is going to be t bar. And so what we do for the actual mean is just rearrange this equation to get t as the subject. So multiply through by 10, we're then going to have 10 lots of the mean of x, x bar plus 2. So that's going to be 10 multiplied by 3.7 plus 2, which gives us 39. So the actual mean time is 39 minutes. Okay, so all we've done here is just taken x bar and substituted in using this idea here. Now the actual standard deviation, so if I call this standard deviation rho t, this is a bit different. The standard deviation is not affected by if we add on or subtract a constant. So the standard deviation isn't going to be affected at all by this -2. So the actual standard deviation, rho t, is just going to be 10 multiplied by the standard deviation of a coded variable x. It's not going to be affected by this minus 2 at all. So that's 10 multiplied by 1.4, which just gives us 14 minutes. Okay, so importantly, when we find out the mean from coded values, the mean does depend on what we've divided by or multiplied by and what we've added or subtracted. However, standard deviation only is affected by what we've multiplied or divided through by, in this case for 10. So just to colour code here, that's all we've done. And that's question 3 complete. Finally, for the warm-up, question 4, we've got this cable, it's a lift, and it's going to lower a mass of 200 kilograms. Whoops, I'm reading that completely wrong, aren't I? No, the lift itself has a mass of 200 kilograms. Inside it is a mass of 55, and the lift is descending, it's going downwards with a constant acceleration. So what we should do first, as ever, is to label on as much information as we can with this diagram. And so I appreciate with your notes there's not a load of space to do this, and so I'm just going to take this over here, just copy this out in my horrible little doodly writing. But make sure when you're doing a diagram, you leave yourself enough space. So what are we told? We're told the crate has a mass of 55 kilograms. Okay, and so therefore we know the force due to gravity on this crate is going to be 55 G. And as a force of habit, unless a question says otherwise, I want you to learn that G is 9.8 meters per second squared. Depends on the question, but the de facto standard value is this. So we've labelled this in. The crate's got a mass of 55 kilograms. The lift itself has a mass of 200 kilograms. And so if we just think of the lift itself as one body as well, then the lift itself has a mass of 200 kilograms. So the force due to gravity from the lift is 200 G. As well as this, we're told that the lift descends vertically, constant acceleration, constant upward resistance of 150 newtons. And so on the lift, somewhere on the lift, we can consider an upward resistance to the motion of 150 newtons. And as well as that, there will also be a tension in the cable acting against the motion. So if we just label this T here, and also we're told the crate experiences a constant normal reaction of magnitude 473 newtons from the floor of the lift. And so on this crate, label this in somewhere, that's going to have a force going upwards of 473. So for part A, we need to find the acceleration of the lift. What I'm going to suggest we do here is just think about forces on the crate. Now there's more than one way of doing most questions. This is no exception. But if we just think about forces on the crate first of all, that's going to help us. So if you wonder what I'm doing here, I'm just sectioning this off for part A and part B to give myself a bit more space. Okay, so considering Newton's second law, we think about F equals ma for the crate. So the resultant force acting downwards on the crate is going to be 55G, which is its rate, minus any forces acting in the opposite direction. So going down is 55G. I'll just label in here. The direction of motion is downwards, as is the acceleration. So the net force acting downwards for the crate is 55G minus the 473 acting against. So that's the resultant force acting down in the direction of the acceleration. And so the resultant force will be the mass of the object, the mass of a crate, multiplied by the acceleration, which we're just going to call A. Okay, now at this stage, we can substitute in what G is. Okay, and so G is 9.8. And so this value here is going to be 55 multiplied by 9.8 minus 473, which gives us 66. And so 66 equals 55A. Therefore, we can divide both sides through by 55. The acceleration is going to be 1.2 meters per second squared. And for part B, find the magnitude of the force exerted on the lift by the cable. In other words, we need to find this tension. So what I'm going to suggest now is we apply Newton's second for the entire system. So let's just think of the crate and the lift as one unified body. Like so. So this is the crate and the lift considered as one. So the weight of the entire system is 200 plus 55. Okay, that's going to be 255 G. Resisting this motion is the 150 newtons, which is mentioned earlier, plus as well the tension in the cable. So the net force going downwards is 255 G minus any forces in the opposite direction. So that's 255 G minus 150 minus T. And that's going to equal the mass of the system, which is 255 kilograms, multiplied by this acceleration, pardon me, which we also know now is 1.2. So let's just substitute in these values and simplify. So 255 multiplied by 9.8 minus 150. That gives us 2349. So 2349 minus T equals 255 multiplied by 1.2. So let's just plug this in. 255 multiplied by 1.2. We get 306. And so with a simple rearrangement of this very simple equation, we therefore get that T equals 2349 minus 306, which to three significant figures would give us 2040 newtons. Okay, so 2040 newtons to three significant figures at least. So that's the warm-up completed. So the new stuff for today is definite integrals. So what we can do, and we're going to show some applications of this in the next lessons, we can calculate integrals between two what are known as limits, and that's called a definite integral. What we've been doing so far is indefinite integrals, where we don't have any limits and we just reverse the differentiation done to a function in a general sort of way. Definite integrals are between two set particular values. So the main distinction here is that a definite integral will usually produce a value, whereas an indefinite integral will always produce a function, and that function is a function which would have been the original function before the differentiation. And so just to show you what the definite integral idea means is just to do some examples with this. So for question 1, we've got the function 3x squared, and we're going to integrate that between the limits x equals 1 and x equals 3. And so what we do here is we integrate, so the elongated s symbol, we're integrating 3x squared with respect to this variable x. Now the limits are x equals 1 and x equals 3. And so what we do, the higher limit we put here as a small 3. The lower limit we put below as a small 1. So the higher limit goes above, the lower limit goes below. And so what we do here is we integrate as we would normally. So we increase the power of x by 1 and then divide through by that new power. And so if we have to do it here, the x squared would become x cubed, and then we divide all this through by the new power, which would be 3. Now 3x cubed divided by 3 will just leave us with x cubed. And think about it this way, if you were to differentiate x cubed, the power would go to the front, and then we'd drop 1 off this power. And so x cubed differentiated would give us 3x squared, which is what we've got here. Now we need to put these in squared brackets. Now this is an important bit of notation. When we're doing definite integrals, we put what we get when we integrate this into square brackets and then put the limits over here, like so. Then what we do is we substitute in the higher limit first into this expression, and so x cubed when x is 3 is 3 cubed, and we minus off what we get when we substitute in the lower limit, which is 1. And so x cubed when x is 1 is 1 cubed. Okay, so all we're doing here is we're substituting in the higher limit, and afterwards we're substituting in the lower limit. So 3 cubed is obviously 27, minus 1 cubed, which is obviously 1, and that gives us 26. And so that's a fairly easy starter example. So that's how a definite integral works. And as we see, it gives us a value, like we mentioned here. It doesn't give us a function. Let's try a slightly harder one. Now, I hope this might look familiar to you. Have a think where you might have seen this before. Okay, I'll give you another clue. It's in these notes. Another clue, it's in this video. Yet another clue, it's near the start of this video. If you've not got it yet, here's the big reveal. This here, just have a look at warm-up question 1 and question 2. So we had this function here, we integrated it and got that it was the indefinite integral was half x squared plus 4/3 x to the power 3 over 2 plus x plus c. And what I mentioned for 2 part c in the warm-up was we never need this constant of integration when doing a definite integral. So that's just saves us having to rehash question 1 and question 2 again. And so we can use this result. So if we integrate between these limits 1 and 0 of root x plus 1 squared dx, we'd write this in square brackets. We'd have half x squared plus 4/3 x to the 3 over 2 plus x. We don't need this, by the way, like I've said. We're going to do this between the limits 1 and 0. And so, like I mentioned before in the warm-up question 2, what we'd be left with here is just 17 over 6. But if you want to try this yourself, by all means. Okay, so I'm going to put, in fact, I'll be maybe slightly more than generous. I'll put in brackets here what you would have got. So that would be half times 1 squared plus 4/3 times 1 to the 3 over 2 plus 1 minus off half times 0 squared plus 4/3 times 0 to the 3 over 2 plus 0, and that would just be 17 over 6 minus 0. So that's the longhand version of doing it. If you don't trust me, just try it yourself. So you get 17 over 6. So the exact integral, the definite integral, between the limits of 1 and 0 of this function is 17/6. The fundamental theorem of calculus, this is one of the most important things in all of maths. Okay, the proof of this is, we're not going to go into it here. If you've got a function f dashed, and if it's continuous, I need to mention what continuous means. So if a function is continuous, without getting into too much detail right now, that just means it can be differentiated at all points. Can be differentiated, or is differentiable at all points. So if a function is continuous in the interval from between a and b, continuous, then what this means is that this function f dashed needs to be differentiable all between every value of x between a and b. So the function can't have anything weird happening to it. So no asymptotes, for example, between a and b. So it's going to be almost always a smooth, literally continuous curve between a and b, with no weird breaks or crazy stuff happening between. So if a function f dashed is continuous on this interval, then if we integrate this f dashed function between the limits b and a, then this is going to be precisely equal to f of b minus f of a, where the function f is the antiderivative of f dashed. In other words, where the function f is what we get when we integrate f dashed with these particular limits substituted in for that value of x. It's much easier when we put it into practice, and in fact the previous example was using this idea here, but this is the formal statement of what is known as the fundamental theorem of calculus. So you need to know what the fundamental theorem of calculus is. Don't worry about any proof yet. So worked example 3. This is the same idea, just with something more complicated looking. And so we need to find the definite integral between 1 and 0 of this absolute beast here. And so if you ever worked in a zoo, or if you were ever a Roman era gladiator, you'd know what you need to do if you've got a horrible beast is you need to tame it. Now we don't have any spears or guns, I should hope not anyway, so the way we're going to tame this is by simplifying this as much as we can and making it look like something which is easier to deal with. Okay, so what I'm going to suggest we do first of all is just take this thing here, the integrand, and just neaten it up, because right now this is just pretty damn ugly. So I'm just copying it out here. So we've got x squared brackets 1 minus the square root of x cubed all over 2x to the minus 1. So let's just, first of all I'm going to suggest we expand this out. So x squared multiplied by 1 gives us x squared. Then x squared multiplied by the cube root of x cubed. Well, what I'm going to suggest we might want to do here, first of all, actually, is replace the square root of x cubed and write it like this. Okay? So we're going to have minus, then if we're multiplying different powers of x, we just add the powers. So 2 plus 3 over 2, that's going to give us 7 over 2. All of that over 2x to the power minus 1. Now when we divide the powers, we subtract, don't we? And so this divided by 2, that's going to be a half of whatever we get. Now x squared, so power 2 minus minus 1, the new power of x is going to be 3. That's a minus, so the next one will be minus a half. Whoops, I forgot the x. What am I doing? Sorry, that's x to the power 7 over 2. Totally forgot, my apologies. And so x to the 7 over 2 divided by x to the power minus 1, the new power of x will be 7 over 2 minus minus 1, which is 7 over 2 plus 1, which is going to be 9 over 2. Okay, and so what we've got here is a much neatened up version of this function which we need to integrate. So in a nutshell, I've just shown that this thing here is equal to this. Now, this is easier to deal with, so let's have a go at integrating this rather than integrating that. So we need to do this between 1 and 0, and it's half x cubed minus half x to the 9/2 dx. So what we need to do here is, as usual, we take this half x cubed, we increase the power of x by 1, so cubed becomes 4, we divide through by the new power. Same deal over here, half x to the 9/2, we do 9/2 add 1, which gives us 11/2, and then divide through by that 11/2. Again, that's going to be between the limits of 1 and 0. Now, still looks a bit messy this, so let's neaten this up. And again, with practice, you'll be able to do this almost automatically and not have to do this as two separate steps. But for now, I'm showing you the steps separately. So half divided by 4, that's going to leave us with 1/8 x to the power 4. Over here, a half divided by 11/2. If you try it with a calculator, if you're not sure, that's what I'd suggest you do in all instances actually. A half divided by 11/2, that's going to give us 1/11, but it's a minus, so minus 1/11 x to the 11/2. And we're doing this between 1 and 0. So first of all, we're going to input 1 for x. So that's going to be 1/8 times 1 to the power 4 minus 1/11 times 1 to the 11/2. Now again, hopefully you'll be able to spot these tricks sooner rather than later. 1 to any power, that's just going to be 1. Then we minus off what we get when we input 0 into this. And again, if you can just sort of have a feel that, isn't that just going to be 0? Well, yes it is. But if you want to, at this stage, just do it the long exhaustive way. That's not going to hurt right now. In time though, you need to spot that if all these terms are functions of x and you input 0, that's going to be equal to 0. But for now, feel free to do it the long way and convince yourself like this. Okay, so if you just input this into a calculator if you'd like, 1 to the power 4 is going to be 1. 1/11 times 1 to this power is just going to be 1/11. So 1/8 minus 1/11 is going to be 3/88. Leave it in exact form as well. Don't be rounding to decimal places when you've got these, unless the question states so. This here is going to be minus 0. And so we just have 3/88. And that's the answer to worked example question 3. Final worked example, please try your own. Worked example question 4, given that the definite integral between the limits of k and 1 of the reciprocal of root x equals 3, find the value of k. Okay, so this isn't going to be too hard. It looks hard, but actually, if you just don't panic, it's not so bad. So first of all, I'm going to say between k and 1 of the reciprocal of root x dx, I'm going to say that the reciprocal of root x is x to the power minus a half. Okay, root x is x to the half. The reciprocal of that will be the same power with a minus sign, or the opposite sign at least. So, if we increase the power of this, minus a half plus 1, that's going to give us x to the half. And then we divide through by the new power of x, as we do whenever we integrate. It's going back to the first ideas. And we do this between k and 1. Bit more space needed, Could just scroll down, but I'm feeling a bit lazy. Okay, so x to the half divided by a half, I'd say we can fairly obviously make this a bit neater and just say anything divided by a half is going to be 2. So we've got 2x to the half between the limits of k and 1. And so if we input the higher limit, k, for x, what we're going to have is 2k to the half, square root of k if you like, then minus 2 times 1 to the half, and that just equals 2k to the half, and 1 to a half, square root of 1 is just 1, so 2 times 1 just gives us minus 2. And we're told that this equals 3, so therefore 2k to the half minus 2 must equal 3. Okay, what we've done so far is we've worked out this and got that, and we're told it's equal to 3, and so we know that this must equal 3. So now we can actually go forward and solve this. So if we add 2 to both sides, so 2k to the half must equal 5. Bit more space. I'm still feeling lazy. Apologies if that disgusts you. I can be disgusting. I hope you forgive me. Zoom. Divide through by 2. So k to the half must be 5 over 2. So therefore k, if we square root both sides, we're now going to get what k must be equal to. So 5 over 2 all squared. K must equal 25 over 4. If you want to write it as 6.25, you can if you really want to. I suggest leaving it in this form. And that's pretty much it for now. Apart from, of course, the usual extra magic ingredient, you practicing on your own. Okay, this is where you need to come in. So page 297, exercise 13D. Try the whole exercise if you're serious about mastering these. It's a really, really crucial concept to get your head around. Try all these. If you get stuck, you know where I am. Send me an email. If you don't want to email, leave me a comment in these comment sections. If your comment sections are looking rather dry, I'm almost getting the impression you don't want to leave me any comments. So let's just massage the ego. Go on, leave me a comment, why not? So try those. Do keep safe, do keep working, and I'll see you soon in the next video. But please do keep in touch. Okay, thanks for listening. See ya.